Hello, I'm Tom Woods. I'm Associate Director here at LASP. I'm pleased to introduce our speaker, Dr. Sam Durrance. He was a former graduate student here back in the 70s, finished up in 1980. He was one of Bart's students, and he went on to Johns Hopkins University, where I was pleased to be able to work with him on some sounding rockets, studying comets and Jupiter EO and other things. And I learned a lot from Sam, and I really appreciate all that he has taught me and all the fun that we had together too. And he's also, at that time at Hopkins, started working on the Hopkins ultraviolet telescope, and they needed some payload specialists, that is, astronauts. And he applied, and he was selected, and he got to fly twice on the shuttle. So he'll, I think, will share some of those experiences as well. And he's now at the Florida Institute of Technology down in Florida, as a professor there, and we're pleased to be able to have him here today to speak to us about LASP and beyond. So, Sam.
Well, thank you, Tom. Thank you so much. And it was a really interesting time we spent together in Hopkins. And today, what I'm going to really try to do is just describe to you the adventure that I was on and have been on for many years now. And I thought I would start today back at, kind of the beginning to give you a feel for, what it was like. I'm going to try my best to share this experience that I've been involved in for many years with you. I grew up in Florida, and I was really not that great a student, to tell you the truth. I was interested in other things, primarily sports racing cars. And the picture in the upper left there is a car that I built. When I was a high school student, I started working on it then. I finished it up a little while after that. And so I was much more interested in sort of following in Enzo Ferrari's footsteps than anybody else's. And speaking of Ferraris, a thing happened is at one point a friend of mine whose family had a significant amount of money, he had a Ferrari called Ferrari 275 GTV4, which is just a designation of a car that was built in 1967. And that's a picture of it, not of one like that, but of it. And I'll tell you about that in a second. He needed somebody to drive it to California for him. So I said, I'm your guy. For some reason, I've gotten interested in drama at the point. So I enrolled in the Pasadena Playhouse College of Theater Arts in Pasadena, California. And I had a friend of mine, George Mason. We got in John's Ferrari, and we drove across the country. And as you can imagine, that was a pretty exciting trip. We took 5 days, but we probably could have made it in one the way we were traveling. So anyhow, I got there and was studying drama. And the school that I was going to had some financial problems, and they closed. And I had met a girl there, and her father was a physicist. And he had a physics friend that I met and got to know, a guy named Richard Feynman, who I'm sure many of you know. And he's a really intriguing guy. And I thought, well, maybe I should go back and study physics. And so I did. I went to California State University, LA. I went there for 4 years. And I was studying nuclear physics at the time. And there was an opportunity to go. The guy I was working for had a former student of his that was working in the cyclotron facility here at the University of Colorado. And so I said, okay. Actually, what happened was I was going to enroll in a couple of places, but I drove through Boulder, and I said, this is the place I'm going to go. I started driving by myself in my little Volkswagen across the country. And so I came here and started that, and that didn't work out too good, and I was much more interested in the space program. And I guess one of the things that I sort of left out is when I sort of transitioned from the Pasadena Playhouse to the California State University was in 1970. That summer is when we landed on the moon. So that was something that was, that I was really interested in, not going to be an astronaut, but just to get involved with the space program in some way. And LASP, of course, was very involved in the space program, and so I sort of started working at LASP. And LASP is really a unique place. I'm sure many of you know that. And I tried to find some pictures from when I was here, but we didn't have digital cameras in those days. And all of our pictures are squirreled away somewhere, and my beautiful wife Becky here probably could find them if I really goaded her for it, but anyway, I couldn't. So I put some of your pictures up here, but I wanted to just talk about my time at LASP and what happened. When I started, there was a control room here, which was kind of an amazing thing, a control room for the OSO 8 satellite, and I started working on that. And there was a guy that was there helping us out, a guy named Dave Stern, who's here, and he was developing a language that didn't have a name or anything at the time. It was just a language that analyzed the data, which many of you probably know sort of went on to become something called IDL, Interactive Data Languages, and Dave formed this company to do that, and I'll get to that again in a little while. So it worked on OSO 8, and then Charles Barth said, well, I got this rocket that's we're gonna launch to look at Venus, and I want you to go down and work with Phil McClintock and sort of start working on that. So I went and did that, and we launched this rocket, which was really exciting. You're launching a sounding rocket. We sort of got a spectrum of Venus. It was a little chancy at the time. We only have about 10 or 20 photons. I'm not sure I made this experiment. But anyway, so we did that. And then I was working with Gary Thomas and started doing some work on atmospheric calculations. And Barth said, no, I think you'd be better off if you got involved with this Pioneer Venus satellite. We're just going into orbit, and we're going to be analyzing the UV spectrum. And so I started doing that, and that was what I did for my thesis, analyze the spectrum of Venus. And it turned out to be really interesting. We were also, of course, they had they were PI or involved in something called the IUE satellite, so we used that to observe the Venus as well. So I did my thesis in that. And then it was time for me to move on, and one of the postdocs that was here had been at Johns Hopkins University, and he noticed that one of the guys there, a guy named Art Davidson, had just won a contract with NASA to build a 1-meter class telescope to be part of a space shuttle project. So I said, well, maybe I can do that. So I decided to go there. The reason I'm sort of going into this is one of the things that's really unique about LASP is all of the opportunities that are available for students, young scientists, old scientists, and it's kind of unique, really, in the world of science. There are only a handful of places that can do what is done here at LASP. I think that the people here know that. The people who haven't been around some place like LASP don't know what they're missing, really. And so anyway, I went to Johns Hopkins, and Art was looking for somebody to do extragalactic astronomy, and I was really a planetary scientist. And so he said, no, I don't think so. But Paul Feldman was a planetary scientist, and he said, well, you should come and work with me. So I did that and worked on a couple of sounding rockets with Tom. We got to know Tom. And then Art's program was running a little behind schedule, and he needed some help, and he came to me and asked if I would be interested in working on HUT. And so I said, of course, I would be delighted. And so we started that, and it turned out that NASA had not just selected one experiment, but had selected 3, and they had combined them into something known as the Astro Missions in Ultraviolet Astronomy. The idea was to turn the space shuttle itself into an astronomical observatory. So unlike the Hubble Space Telescope, which is a complete self-contained satellite observatory, the Astro Observatory used the shuttle as part of the observatory. And it was completely integrated into the operations of the shuttle. It was mounted in the cargo bay on a pointing system. The 3 telescopes were co-aligned and operated like a single observatory. And so it just made sense to hire somebody who understood the observatory itself, had really developmental knowledge of the telescopes, and understood the scientific objectives of the mission. And NASA agreed, and so we went through a selection process, and eventually I was selected as one of the astronauts to fly with this observatory whenever it flew. Originally there were 3 flights planned, and we were planning 3 more, and that's before the shuttle ever flew, because I graduated in 1980 and it flew the first time in 1981. And so the flight rate didn't turn out to be quite what we thought it would be, and so we didn't get the 3 flights. But anyway, that's what happened. So I went there and I started working on building this observatory. And I want to show you a few slides just to give you a feel for what it was like. I won't go into any real technical detail unless you have questions, and I'd be delighted to. So this is the Astro, this is HUT, the telescope we call HUT. And that's me a long time ago, making some optical measurements. My job is really the overall optical design and the assembly and alignment and verification of the optical system. And I'm making some measurements during the time that we're assembling the telescope itself. That cylindrical structure you see there is the primary structure of the telescope. And one of the kind of funny things that happened was we had to design it so it would operate over a fairly large temperature range. And so the material that we selected has a very low thermal expansion coefficient. It wouldn't stretch or compress very much when the temperature changed. And it was originally flat sheets that had to be rolled into this cylindrical shape. And the rings at the top and bottom were originally long I-beams that had to be rolled into that shape. And the only place we could find that had a machine that was large enough and strong enough to do that was a garbage truck manufacturing outfit in Philadelphia. So this very precise optical space telescope was built by a garbage truck manufacturer. Another kind of funny thing that happened is that if you look in the lower right there, that's when the telescope was finished. And we built it in a basement laboratory at Hopkins, which is an old university. And it's sitting on a cart that has trolley, had wheels on it so we could roll it around, and had a cover that goes over it. And as we're designing it, that cart kept growing. And we knew at some point we had to get it out of the building. Right? And finally, we got to the point where, well, it just may not make it. So we made up a little mock-up because we had to go out of the doors, the double doors in this laboratory, into the hallway, around a right angle corner to get down to the loading dock. And guess what? It wouldn't fit. So there were really a lot of smart people working on this, and I didn't quite think of everything. We had to call the facilities to bring over a hydraulic jack so that they could prop up a 5-story building and shave off a corner of this post so we could get the telescope out of the building. We did get it out of the building, however, and we moved on. I'm sort of doing a parallel track between the astronaut activity and the assembly of the telescope activity, because that was really my job to do that anyway. So I had already been selected by this point to be one of the astronauts to operate when it was in orbit. And these are some pictures of the mirror, and there's an interesting story about this too. You see there myself and a graduate student coating the mirror and putting it in a tank, or not coating it, it's been coated, and we have it in a tank that we're going to measure the reflectivity. It would rotate, and we had a spectrometer that would move in and out like that, so we could just measure the reflectivity of the mirror. The mirror was held into the telescope with a clamp assembly that you see in the center there, sort of the bottom left part of the picture. That clamp would come apart, and you put the mirror in there and set it on, and then you bring the clamp down together, and you bolt the clamp together. And there were 3 arms that the mirror set in between, and there was a bolt and a nut, and so there was just really a pressure compression that held the mirror in place during the vibration of launch. And that bolt, which is right here, had to be torqued to 150 foot-pounds of torque on a piece of glass. And that seemed like a lot, and it turned out that I was the guy who had to tighten it. And by that point, I'd been selected as the astronaut to fly with it. And we do this in a clean room with a full bunny suit on, like this. And it also has a load cell on it, so we were not relying totally on the torque wrench. We had a torque wrench, so here I am leaning out over this $200,000 mirror with a wrench, tightening like this, knowing that if I broke the mirror, there goes my ticket to launch, right? That was kind of a hair-raising experience. The selection process started in 1983, and this observatory had 3 telescopes on it, and it was decided that they would select one person from each of the primary instruments to hire as astronauts, to bring into the astronaut corps, to fly with this instrument whenever it flew. And where it's shown in the upper left there was myself from Hopkins, Ron Priest from the Goddard Spaceflight Center, and Ken Norzik from the University of Wisconsin. That's where the 3 instruments were built. We were assigned the rest of the crew. The idea was that 2 of us would fly on any given mission so that we could operate 24 hours a day. And so Ron and myself were selected for the first flight. And the rest of the crew was assigned, you see in the lower left. We were selected in the summer of '84. The crew was assigned, the full crew was assigned right after that. And myself and Ron were selected for the first flight. We continued to develop the observatory, because that was our job. These are just some pictures of the observatory. We finished it in January. We did the thermal vacuum test. Oops. Sorry. This is just some pictures of the training. So we spent most of our time in Houston, or in Florida, or in Alabama, training for the flights. Some of the training was a lot of fun. A lot of it's sort of, workbook training. You're learning how to operate a bunch of equipment. But there's some of it that's fun. You get in the upper left, you see us coming back from sometime when we were flying on T-38s, so you get to fly a small jet trainer, T-38, and the training syllabus says that that's for you to experience a high-stress flight environment, and you really do that. They barely go over the speed of sound, so we get to go travel faster than the speed of sound in those. But it's a highly maneuverable aircraft. It has what we call a full deflection aileron roll rate, where if you just push the stick all the way to the left like that, it rolls at 720 degrees per second. That's twice around in 1 second. And it's so fast that your brain doesn't perceive that you're rolling, because you want the horizon to be horizontal. So all you see is right side up, upside down, right side up, upside down, right side up, upside down, like that. Anyway, some of the training was a lot of fun. We continued working on the observatory, the telescopes themselves. We completed the observatory and ran it through a thermal vacuum test at Goddard. You see it here on the right, being lowered down into a tank. We did that in January of 1985 and delivered it to Florida. In Florida, it was integrated with the rest of the telescope, and it took about a year to do that. The crew, of course, continued to train and to participate in all the integration activities of the observatory. We had everything ready. We had tested the entire observatory. You see it in the lower right during the final test. We ran a mission sequence test, what it's called. We pick a 24-hour time slot of the mission itself, and we run through all of the activities that are going to occur in that 24-hour period. So it's all tested and ready to go. It was taken over to the orbiter processing facility and installed in Space Shuttle Columbia. And we were trained, ready to go. We were just waiting for the next flight to get off the ground. But our first flight was scheduled for March of 1986, which was the flight right after the Challenger accident. So we were on deck waiting for that, and that didn't happen. So we had to wait quite a while after that. It took 2.5 years to recertify the shuttle system. There was a recertification flight, And in the early days of the space program, we were flying Department of Defense satellites and there were 3 of them that were sort of backed up on the manifest, which had much higher priority than a purely scientific mission. And so we just kept getting bumped down the manifest. And then we had some problems with the telescopes themselves. We had to fix some splices in them, and it took about 6 months to do that. So we kept moving down the manifest. We weren't ready to fly again until the spring of 1990. So this is us. We're getting ready to fly spring of 1990. And I'm going to go into a little bit of detail about the few days before liftoff. And you'll see why in a minute. You've trained for a long time. And you go into a medical quarantine 7 days before liftoff. We do that down at Houston. We move into crew quarters. You can have your spouse come by and have dinner. You're not allowed to see anyone under the age of 14, so like our children at the time were younger than that, so I couldn't see them. This gives you a little time to rest. You've been training so hard, and you're not going to learn anything more in the 7 days before liftoff, so it's a kind of a buffer, lets you rest a little bit. We also use that time to shift our circadian rhythm because we don't want to reach orbit and have jet lag, and we're a 2-shift operation, so one team is split up into 2 teams, and one team is by definition night shift Houston time. And in the crew quarters here, they set up a room with bright lights. Brought this guy down from Harvard named Dr. Zeisler, who had showed that you can shift your biological circadian rhythm with the treatment of very bright lights. So NASA hired him. He came down and brought a bunch of graduate students, and they set up a room with every square inch of the ceiling filled with fluorescent bright lights. There was a white canvas down on the carpet. The walls were white. They put white paper on the tables. And the crew that was the night shift would go in there during the night and turn the lights on and stay awake all night long, and then go in a dark room and sleep. And that shifts your circadian rhythm biologically. And that's the first time it had been done as an operational system, and so they were measuring our circadian rhythm indicators, and you could see them shift, just like that in one sitting of these bright lights. We then fly down to Florida 3 days before liftoff, and we fly down all together in the T-38s, and so we fly at a time when both shifts are awake, either breakfast or dinner for one or the other. And there's a crew quarters at Florida. We move in there, and they have a room with bright lights so you can get your fix of light whenever you're supposed to get it. And there's some traditional events that occur, like your spouse, my wife Becky, holds a reception for all your friends and relatives that have come from some from very far away to see the launch. You can't go because you're in quarantine. We set up a phone and we talk to all our friends. And then there's a really neat event is that there's a beach house on the Kennedy Space Center. When the area was taken over to establish the Space Center, there was a small beach community there. They took everything out but one rustic old 1950s era beach house right on the beach, right between Launch Complex 40 and 41. And crews have been able to use that since the early part of the space program to relax. You can have your spouse out to visit, you have dinner together with the crew. It's just some real nice, relaxing time before you go do something a little risky. And there's a tradition that there's a barbecue that's held. The mission management team holds a barbecue for some of the mission management folks, and you can invite your spouse, and you can invite 4 of your closest friends or relatives. So you can invite your parents and your brothers and sisters, which is a bit of a quandary at times because, for example, I have 2 brothers and a sister and 2 parents. I can invite 4 of them. So something has to happen. And fortunately, they all have to go get a physical before they come out so that they can be in contact with you. And fortunately, my younger brother had a cold, so that was settled. So we do that, and this barbecue is really nice. It's a rustic old beach house, and we were a night launch, and so we were out there at the night before launch, and you can walk out on the porch there and look about 1 mile north where the shuttle is sitting on the launch pad with the rotating service structure rolled back and all these big xenon lights shining on it. It's just an awesome experience. And so that's over. Then we go back to crew quarters and go to sleep. And 12 hours before liftoff, they start the taping process. That's where you fill the big external tank with liquid oxygen, liquid hydrogen, and it leaked hydrogen gas in the aft engine compartment, all under the shuttle itself. Very dangerous situation, so they just stopped the tanking process. Sent us back to Houston, picked up our family, and took them back to Houston. So we got out of quarantine. They find the problem, and they fixed it. So they said, get ready again. So we go back into quarantine and shift our circadian rhythms, fly down to Florida, have the reception, have the barbecue, start the tanking process, and it leaks again. Back to Houston. We got really good at that. We did it 5 times. And between the 4th and 5th attempt, it was determined that they couldn't fix it on the launch pad. So they rolled Columbia back into the vehicle assembly building and rolled Atlantis out to the launch pad and launched it while we're waiting. That's kind of a neat picture. This is the only time this has ever happened. 2 shuttles crossing in the night on the crawler way, one going in and one going out to the launch pad. So they launched Atlantis, and they finally got Columbia fixed, and so we were going to get ready again, but then a hurricane came along. We had to roll the vehicle back into the vehicle assembly building, wait for the hurricane to pass, roll it back out, get ready again, go into quarantine. You know, we thought it was like Groundhog Day. We're going to do this for the rest of our lives. You can imagine. But we did. We finally launched. We launched early in the morning, December the 2nd, 1990, 1:49 a.m. And that is one wild ride. Has anybody ever ridden the shuttle launch experience down at Kennedy Space Center yet? A few of you. That's kind of a neat simulation. It simulates the events that occur and when they're going to happen, but it really does not quite simulate the violence of the launch itself. It is the most violent, dramatic event I have ever experienced, and by far. The launch sequence goes something like this. You have the shuttle bolted down to the launch pad. There are 4 bolts on each solid rocket booster. And the bolts are 10 centimeters in diameter and about 1.5 meters long. Huge bolts. There's a nut that goes on the outside of those, and that holds it in place. And there are 4 of them on each of the solid rocket boosters. You start the main engines on the shuttle, the 3 main engines, and you bring them up to full power while it's still bolted down to the launch pad. Well, the shuttle is offset relative to the boosters, and so there's a torque. And at the altitude where you are in the crew compartment, it bends the shuttle over 6 feet to the north. So it pushes it 6 feet to the north. It springs back. We even have a name for that. It's called a twang maneuver. Twang. And when it gets back to vertical, you ignite the solid rocket boosters, and it takes 0.6 of a second for them to come up to full power, 3 million pounds of thrust each. The 3 main engines provide 1.2 million pounds, so you've got 7.2 million pounds of thrust. And the vehicle weighs 4.5 million pounds at that time. So the thrust to weight ratio is very high. And it feels like somebody ran into the back of you with a Mack truck or something. Wham, like that. Leap up off the launch pad and starts this fairly violent, jerky motion. It's not vibration. It's like as the thrust vectoring system is correcting for the attitude of the shuttle to keep it going straight. And you also, so the thrust picks up, not gradually, picks up very rapidly to 2.5 Gs. The main engines then throttle back as you go through the maximum dynamic pressure. You're still in the atmosphere, and the pressure is building up so it would exceed the stress limit of the vehicle. So it throttles back the main engine so you feel it relax. Then it picks back up again. You go upside down, so you're upside down, being jerked around like crazy, pushed back into the seat. At 2 minutes, the solid rocket boosters have completed all of their, burned all their propellant, and so they're jettisoned. I'm sure you've seen that on TV, right? They sort of majestically float away from the shuttle. There's nothing majestic about it inside. You hear a very loud explosion and a big red flash on the outside, and the thrust immediately drops from 2.8 to 1 G, back down to 1 G, which tends to jerk you out of the seat like that. And you're in really tight. I mean, you've got the seatbelt on really tight, so you don't get jerked completely out. The main engines burn for 6.5 more minutes. They're really smooth. It's like getting on an electric drive. So all this jerky motion is gone. And the thrust is very gradually picking up. So it picks up from 1 G to 3 Gs. And the last minute of the flight, you're at 3 Gs, which is not a whole lot, but it's sustained for a minute. And it's enough because you've got on about 100 pounds of gear. So you've got on a pressure suit and a parachute, and all that weighs about 100 pounds. So the force on your chest, if you can imagine someone, say, weighing 250 pounds sitting on your chest like that, that's kind of what it's doing. So you're going, the last minute of the flight, kind of everybody's doing that. And all of a sudden, in less than a second, it goes from that to absolutely nothing. Right? No force at all. Your stomach comes up in your throat, like going over a wild roller coaster ride. Your arms float up in the air, and from that point on, you're completely weightless. So you release your lap belt and just float out of the seat. And you feel instantly like Superman. You fly around wherever you want to go, and you're completely free to move around. It's not like being underwater where there's viscous stuff. You just propel yourself across the mid deck. It's quite a ride. But then you're in orbit. And this is a picture that I took out of the rear window of Columbia. About the second day or so in orbit, the first couple of days, I was so focused on what we were doing that I saw this, but I didn't really let myself, think about. What an amazing thing that we were doing. There are many, many, many smart people that worked on this over the years. By this time, I'd worked on it for 10 years. We were in orbit in 1990. I started working at Hopkins in 1980. And everything was working like a dream for a while anyway. And it's just an incredibly rewarding experience. And it was clear from all the we were seeing in orbit, clicking off observation after observation, which happened really fast in orbit. I guess everybody here at LASP knows that, but most people don't. You go around the Earth once every 90 minutes. That means you have a sunrise and your stars rise and set in about 30 minutes or so. And in orbit, you can observe during the daytime portion of the orbit because it's pitch black above you. It's very bright below you, but there's no atmosphere, significant atmosphere above you to scatter sunlight into your field of view. So you can observe both night and day. So you observe anywhere, we would observe anywhere from 3 to 5 targets in every orbit. And you do 16 orbits a day. And it was working like a dream. But there's really nothing that can prepare you for what it's like to see the Earth from that perspective. And I will kind of try to finish this tonight on a little, talk to you a little bit about the emotional impact. But it was just working like a dream. We had some problems that occurred a little later on this flight that we had to work around, but we did. I'll maybe talk about those later. But the other thing is you're weightless the whole time. And weightlessness is kind of a nuisance at some point because you have to sort of adjust the way you do things, because if you, for example, if you want to open a locker and you reach up and grab the locker to open the locker, all you do is pull yourself to the wall. You have to get used to using 2 hands to do everything. But it's like maneuvering around. You forget that you have to do that and you just do it. And when you move around in weightlessness, you have to push off of one surface and you translate linearly until you get to the other surface and you stop. But you forget that too. And you think that you're just going to go somewhere, you just think you fly over there. So you literally think you were flying, fly around. There's another thing is that an interesting discovery for me personally was that in weightlessness, you still have this psychological perception of being right side up. We have that here. We all feel very right side up. We have a floor. It looks like a floor. We have a ceiling. It looks like a ceiling. Now, in orbit, there's no official up or down, but you're in an enclosed system. And in the shuttle, it's designed with a floor. It has a floor. It has ceiling. The ceilings have lights in it. But if you look at the lower left there, Bob and Vance are oriented with their feet towards the floor of the mid-deck. They have their foot in a toe loop or something to hold them in place. And so to them, that looks like the floor, and the ceiling looks like the ceiling. Ron, however, has floated around the other way and has his feet hooked on a toe loop on the ceiling. And as soon as you do that and stabilize yourself, it's really funny. It's like a bit flips in your brain, and you go, and you feel literally, psychologically, right side up. And you'd swear that what's by your feet was the floor. It looks and feels to you like the floor. And whatever's over your head looks and feels like the ceiling. And you carry that with you wherever you go until you change it. And so it's, I don't know what it is. It's like we have to have a right side up, evolutionary development. We have to be right side up. And there is no right side up, but you still have to have one. And so it's kind of fun to play with. I used to like putting on my Walkman and listening to music and try to dance, which is kind of cool because you just sort of twist about your center of mass. That's pretty well. And the other thing is I put on something slow and close my eyes and try to get out in the middle of the middeck, and you just sort of gradually drift around, and every now and then I'd open my eyes and you feel just really disoriented. And all of a sudden, you feel right side up, where your feet were was the floor, and it will look like a floor. Anyway, it was very interesting. Just some pictures of in orbit. I took along some mementos. I have one there. I've got a picture of a little thing we had to tell Becky and the kids that I loved her. See, that's actually just floating there in front of me. I also, unfortunately, I didn't put it in here, but I have with two other crew members who went to school at the University of Colorado, and we have a little flag floating in front of us with our names on it and CU on it. So I'll get that to you. It was an amazing view. The view was just unbelievable. I'll talk about that a little more in a minute. We were in orbit for 9 days, operating the observatory. We landed out in California. I had a graduate student and a postdoc at the time that were at the Las Campanas Observatory when we were in orbit. And so I wanted to get some pictures of it. So this is a picture of the west coast of Chile from the shuttle Columbia. And in the picture, in the sort of lower or the mid-left part of the picture there, all of the large ground-based observatories in the southern hemisphere, or at least in Chile, there's some in Australia, that are in that picture. And Dave Galmaski and Mark Hyman were down there at the Las Campanas Observatory. They were, of course, asleep because on Earth you have to do astronomy at night. And during the day. I tried to get a close-up picture of it, but I never succeeded in getting a close-up picture of the observatory. But they're in this picture. What other pictures do I have? Oh, this is a picture I love. This is a picture that I took at night. And if you look at this, there are a couple of things you can see. One is there's a thruster firing. There's a little thruster firing here. And when that thruster fires, it's actually kind of hard to capture that because they fire randomly. What we do is set a dead band in the attitude control system. And whenever the shuttle drifts to that dead band, it'll fire a thruster to correct it. And you can't, well, you could predict it if you wanted to, but you normally don't. So you have to have the camera ready to take that picture. And when the thruster fires, you get this flash behind it. And I believe that's ionospheric recombination radiation, which is catalyzed by these heavy particles that come out from the thruster itself. So you get a three-body recombination process with the ionospheric radiation. And if you look down at the solid Earth, that's the air glow layer up above it. And that air glow layer occurs for a number of reasons, but one of those is the three-body recombination of atomic oxygen into molecular oxygen. And so it's kind of neat to see both of those in the same picture. And it also gives you a little bit of a fiducial mark, because that air glow layer occurs at 100 kilometers above the surface. And so that is a distance of 100 kilometers. That might sort of stimulate a whole other thing in your mind, is that, wow, the livable portion of the atmosphere is only 1/10 of that. So it's about the width of that line, actually. So from this perspective, the livable portion of the atmosphere is no more than, the width of a pencil that held at arm's length. Just a tiny little film around the surface of this planet. I knew that intellectually before I went there, but it's just something different about seeing it. I don't know. It's interesting. We landed out in California after 9 days. they were doing some experiments on us. Becky was out there, and the kids were out there, and they wanted to make some measurements, so they took some data on us. They were doing some muscle performance experiments and the heart rate experiments and a number of other things. And they wanted to do some tests 12 hours later, so they put us up at a dude ranch out there. We went to this dude ranch, and the next morning, Susan at the time, our little girl, we have a young son and daughter, and she was about 4, something like that. And she wanted to ride a horse. There was a horse there. And I thought, oh boy, this is great. I'm going to get a picture of this. So I had the camera, and it was getting a little cold. I had my coat on my other arm, and I had the camera in the other hand. I said, well, I got to get a picture of this, but I'll put my coat on first. So I let the camera go. I'm assuming we're going to float there because for the past 9 days, and when I do that, I just float there, right? And I'd forgotten that you know, that's one of the things that you're told your particular spouses, so don't let them anywhere near the good china when they come back. We didn't get that picture, unfortunately. We ferried Columbia back to Florida. We took the telescopes out. There had been some significant improvement in coating technology for ultraviolet reflectivity. We originally had the mirrors coated with osmium, which had a reflectivity of about 20% in the ultraviolet. And there was a new technique using silicon carbide that had a reflectivity of 40%. And so it was worth it for us to take the telescope apart, and there were 2 optical surfaces, the primary mirror and the grating, and recoat them with silicon carbide. And we improved the sensitivity, the throughput, by about a factor of 3 when we did that. So it took us 2 years to do it, but it was worth it to do that. We put it back together, we reintegrated it, and we installed it in the Space Shuttle Endeavour. This is the crew. This time there were 2 women on board, and I was on the girls' team for this. So we split up into 2 teams, and Tammy Jernigan and Wendy Lawrence and myself were on one of the teams. So I was on the girls' team. We launched again in March of 1995. This is us launching an Endeavour, and it was just as exciting the second time as it was the first time. It's just you know, just the most amazing feeling of power you can imagine. We were in orbit for 17 days, which is the longest flight of the shuttle program. And if you look in the upper left image there's John Grunsfeld and myself. We have a little laptop computer, and one of the things that I wanted to do was take the copy. I had a license for IDL, and so I took it into orbit with me. And we got one of the guide stars that we're looking at, and we have a spectrum of it on there, and got this picture, and brought it back, and made a big plaque of it, and John and I signed it and gave it to Dave Stern. So that was really kind of a nice whole thing. He helped me understand IDL to begin with, before it was IDL. So we were in orbit for 17 days. We landed out in California. Just an amazing experience. This is a little video that is kind of a collage of the 2 flights that I was on, showing the launch phase, on-orbit phase, and the landing phase. So that's me, actually, a long time ago. This is the crew quarters at Kennedy Space Center. Just before launch, we have what's a traditional breakfast. Not sure why it's always breakfast after about 8 at night. It always is. We go from there down to the suit room to put on our launch and entry suits. There are suit technicians here, run the pressure check, make sure everything's functioning properly in the pressure suit. Walk out of crew quarters, get the van, drive us out to the launch pad, about 10 miles. Drop us off there. We get in an elevator, go up to the 195 feet up, we get on the shuttle. It takes about an hour to strap us in. Meanwhile, the firing equipment you'll see here, the test team has been working for 72 hours to get the shuttle set and ready to go. Now, 4 minutes before liftoff, we start the hydraulic system. Make sure all the flight surfaces will maneuver to their full range, including the engine bells and everything. The ignition sequence, we start 6 seconds before liftoff. Ignite the 3 main engines on the shuttle, bring them up to full power.
4, 3, 2, 1. And booster ignition and liftoff of Endeavour on a voyage to view the universe.
Absolutely no doubt in your mind we're going somewhere in that house. Not at all. The first 2 minutes is kind of rough. The solids are burning. That's mission control in Houston, Texas, where the mission is controlled from. But after 8.5 minutes of powered flight, then you're in orbit, and you're going to stay in orbit until you fire the orbital maneuvering engines to orbit days later. We don't waste any time. As soon as the main engines go off, we go right to work and start moving the payload towards and start making observations. Tammy Durrance and myself activating the Astro Observatory on the aft flight deck of Endeavour. The windows look out on the Carpet Bay, and that's what you see out there. That's Astro getting ready, and its gimbal system getting ready to start making observations. And that's the port side of Columbia, and that's me, and that's where the controls for the observatory were. There's 2 video monitors. We got field cameras and 2 telescopes, so you see the star field. Taught a physics class in orbit, and Jeff did too, but he brought along a tie so that he could upstage me. Only tie ever in space. Those are the bunks where the off-duty crew sleeps. You can block out the light and the noise for the crew that's on duty. That's how we get up and go to work every day in space. We're a disciplined crew.
I think she's going to pass up some food to Sam. He doesn't get an opportunity to come down much experiment. The telescope keeps him so busy. That's the only way to do it. Wait, this is great. Well, just Sam's got to go back up to work.
So that's the mid deck and the galley where we prepare the food. We are having lunch. At least Tammy and I are having lunch. Wendy's having a little trouble catching hers.
Free-floating fluid.
That's water, just floating there.
Jeff was a little thirsty, I guess.
Here Jeff and I are combining water out of 2 separate water containers to watch the surface tension. Pull it together in a roughly spherical little ball with sort of low oscillation modes floating there between us. We were trying to keep it between us and sort of blowing it gently. It would wander off. Never get enough of this looking out the window, looking back at Earth, taking pictures, trying to capture what it is. That's a view out that window of Endeavour.
Seeing some amazing lightning from our downlink cameras, Endeavour.
So the flashes you see on the left part of the image there was a lightning storm over Alabama, which looks 2-dimensional to you.
Yeah, it's better with your eyeball.
The other lights are city lights, of course. The Earth is defined by city lights at night, orbiting across the world. The next to the Earth. Here I got the camera pointing straight down. A little bit of feel for how fast we're actually going. They were going 5 miles per second. Every second, over 5 miles. timeline because you've got to find everything that's been floating around for days and days, put it away, make sure it's in a locker, hide it somewhere so it doesn't become a projectile. Put our launch and entry suits back on, and get ready to come back. This is Endeavour gliding for landing out of California. We've been in orbit for 17 days. Traveled over 6 million miles in that time. Executes a perfect landing on Mars without ever taking.
Made your touchdown?
Houston, now controlling the flight of Columbia. Houston, Columbia is in the roll program. Roger, roll, Columbia. Columbia completes the roll in 30 seconds.
Amazing space vehicle. And I'd like to close with trying to relate to you a little bit about the emotional impact. And the only way I can do that is I wrote something about it, and I'm just going to sort of read that for you. So this is kind of my thoughts, really. Riding a rocket into space, or the exhilaration of zero G, the satisfaction of operating the Astro Observatory, or the emotional impact of seeing Earth from orbit. How can I possibly describe spaceflight? Here are a few thoughts I had just before I took this picture. The Astro 1 mission, December the 2nd, 1990, floating freely near the aft window of the Space Shuttle Columbia. Orbiting 220 miles above the Earth, looking out over this magnificent spaceship and seeing Earth far below. So many talented people had worked so hard for so long to make this moment possible. I felt extremely proud to be part of it. I was well prepared for all of the technical aspects of our mission. But nothing could have prepared me for the sight below. It was broad daylight somewhere over the Atlantic Ocean, far below. The Cape Verde Islands were speeding lazily by. An intricate pattern of brilliant white clouds laced the deep, rich blue of the ocean. The African continent was rapidly approaching from the horizon. The thin blue line that defines the extent of the atmosphere was visible just over the bright rim of the Earth. We were a lone, magnificent flying machine careening through the black void of space at 5 miles per second, and yet somehow, at the same time, floating effortlessly above Earth. Soon our orbit carried us past the terminator. The setting sun created a brilliant light show unmatched by anything I have seen. The full moon cast a beautiful, serene glow over the Earth below. The air glow layer, out on the horizon above the limb, seemed to blanket and protect the cities below whose lights drifted silently past. It was time to go back to work. We came to observe the stars, but I couldn't keep my eyes off the Earth. The amazing light show of sunrise or sunset flashed by every 45 minutes. I saw continents and oceans scroll by at a startlingly fast pace. I could see the imprint of geology on a global scale that seemed to make it come to life. And I saw the impact of humanity on this delicate, isolated island of life, set in a black, black void of endless space. I was left with a sense of the beauty fragility of planet Earth and a feeling that it is imperative that we protect and preserve it. I left Earth with great anticipation, with great excitement, and a little apprehension. I returned with a new feeling of wonder, a new perspective, a space traveler's perspective. It is something I will always have. Thank you. Be delighted.
Just wondering, we saw the water floating over. I wonder what the humidity is inside. Will that evaporate? And also, the junction, is it supposed to get trashy with things falling around? And on top of that, what about motion sickness? Do you ever get that? Or does anybody ever get ill with it?
That's a bunch of questions.
I know.
Okay, the first one is the humidity. It's a closed environment, and so there are humidity separators in the environmental control system because you actually put out a lot of water vapor from your perspiration and your breath, and if you didn't take the humidity out of the air, it would hit 100% very shortly. And so us putting out the water, we didn't get in any trouble for that, for doing that. That really didn't add much water to the handle, to the load for the humidity separator system. And we typically have the humidity set at about 50%. So we set the temperature, the air temperature at 70% and the humidity at 50%. So it's fairly nice. And as to the environment itself, you have to be very careful about cleaning it. We have a very strict routine of cleaning it, cleaning all the walls and all the surfaces because bacteria will grow very rapidly. So every day there's a cleaning process where we wipe down the walls and try to control the bacterial growth. And there were a couple more questions in there too. What were
Motion sickness
motion
and
sickness.
other illnesses.
The motion sickness on the 2 flights that I was on, there were only 2 crew members that got any significant motion sickness. On the first flight, I didn't get any at all. I mean, just nothing. The second flight, I had a little bit of uneasiness and motion sickness. And the only difference was the first flight, I went to sleep when I got into orbit. And the second flight, I went to work when I got into orbit. And I think that had a little effect because I had to work a 12-hour shift and the motion sickness symptoms because your primary balance mechanism is through the fluid in your inner ear, your semicircular canals, and the fluid floating around in them gives you your acceleration. If you do like that, the fluid moves like that. And the primary balance mechanism is through the otolith glands that sit on, one of them sits on a plane that's facing down and one is on a 45-degree angle. So it gives you your balance. When you reach orbit, that all floats, and so you get nonsensical information from your primary balance mechanism. But your brain, of course, is amazing, and it just turns it off. So that program crashed, so I'm not going to use it. And so there's really there's a little bit of uneasiness when you first get into orbit, but it goes away, and it's really not an issue at all. It was kind of overplayed, I think, in the early days of the space program, because if you do have motion sickness, it only lasts for a day or so. But if the mission is only 3 or 4 days long, then that's a significant amount. And the other illnesses, there were, I think, more headaches than I was used to having in orbit. So we had plenty of medication on board. In fact, that's one of your. There are a lot of weird things you do during training, and one of them is you have to test a bunch of drugs. So they give you a bag of drugs and tell you to test them to see if you have any adverse reactions to them. And it's funny, but some of them are sleep medications. And one of my crew members, one of the side effects for one of the sleep medications was possible loss of short-term memory. And one of the crew members, we were doing a simulation in Alabama, and we went home at night and tried our drugs. So he tried this sleep drug, and the next morning, during the debrief of the simulation, he all of a sudden said, "How did I get here?" He literally had no of putting his clothes on and driving to Marshall. So that was a definite, don't take that one anymore. Yeah.
You did a phenomenal job detailing how crazy it is leaving Earth.
Ah.
How is it coming back to Earth? Entering the
Yeah, sure. The re-entry on the shuttle is very gradual. There's no large deceleration shock like there is with the Soyuz capsule or the blunt nose re-entry vehicles. And for the re-entry, you of course you have to commit halfway around the world. That's when you fire the orbital maneuvering engines, and that lowers your orbit to within the atmosphere when you get around the Earth, and the atmosphere slows you down. And you extend the time that you go through entry interface on the shuttle because it's a glider, so it has a lift to it. And so you don't feel at all when you're getting back into 1G. In fact, the only thing the commander will call out, okay, point 1G, and then a little while later, point 2G, and you're still almost floating at the time. The only thing you notice is that your cue cards and things like that, which normally you let go and they stay there, will start gradually moving down towards the floor. So there's now a real floor, a real down. And so you feel that. So going through entry interface, you don't feel much of anything. It's kind of visually interesting because you come in at a 45-degree angle of attack, and you're ionizing the gas, and that glows, of course, and it comes back together up by the vertical stabilizer. If you look back, it's not like ropes of fire dancing up around the vertical stabilizer. But you feel nothing, really, until you get into the landing area. And when you get back in the landing area, you execute typically a 270-degree turn. You cross the runway. So imagine if this is the runway here, like this. You cross the runway, and you do turn 270 degrees and land like that. And that turn, you come in very high. You're at about 50,000 feet, and you're traveling at the speed of sound, just over the speed of sound, when you cross the runway, and you come down and land after that. That turn is about a 1.5G turn, and you really feel that after having been weightless for a long time. But then both of the flights that I've been on, the main gear, you didn't even notice that it touched the ground. It just greased on the runway. The main gear, the nose wheel, that slaps down pretty hard, so you feel that whack like that when it goes down. But it's the sensation is nothing like launch. It's very, very smooth compared to launch.
What happened to those 4 bolts?
Oh yeah, that's an interesting perk. Okay, the bolts stay. Thank you. The bolts stay on the launch pad. The nuts are split in half, and they're carried up with the solid rocket boosters. They have a cover on them that captures them because you don't want the nuts falling off and getting something. So the nuts are captured on the solid rocket booster. The solid rocket boosters are parachuted back into the water. They hit about 150 miles off the coast of the Atlantic, and there are 2 ships out there waiting for them. They bring them back in. They take the nuts out, among other things. I mean, they clean up the solid rocket booster. The nuts, they take them out, and they've been split in half. Because there's a shaped charge that fires on 2 facets of the nut, just split in half like that. They polish them up, and they turn them the other, put them around like this, and fasten them to a little board, and put a plaque on it that has the closeout picture showing that nut on the Columbia, and on the other side is a little thing they give them to the crew. And it's like a bookend. So it's a bookend of the nuts that were on, so I have 2 of them. One that was the nuts from Columbia, and one that was on the nuts from Endeavour. That's a neat bookend. Lots of questions. Let's go back.
Just going forward after the retirement of the shuttle, where do you think this country's next human spaceflight goal should be?
Oh, you mean should we go back to the moon, or should we?
Yes. What do you think our next objectives in space should be from a human spaceflight perspective?
Yeah. Well, what you get is my personal feeling about it. And personally, I believe we should go back to the moon. I mean, I believe we were on the way to do that. It was certainly not funded properly. But I believe we should go back to the moon and set up some sort of a, more or less a research activity on the moon itself. Going out and bringing an asteroid back, that could be fairly cool too. That's sort of a kind of a neat thing to do, drag an asteroid back so we can play with it, I guess. But the evolution that we're going through now, where we've stopped flying the shuttle, it's kind of sad to see that, but it was a very expensive vehicle to fly. And moving to commercial transportation, and the commercial companies are quite capable of providing that kind of transportation, and I believe can provide it at a significantly less cost than NASA. Certainly less cost than we're paying the Russians, and we pay them $70 million a seat to get our astronauts into orbit now. And that activity is moving along fairly well. You know, they're already providing cargo to the International Space Station, and the crew capability will probably be realized in another 2 or 3 years, which is a long time. I don't want to wait that long, but you know, that's the nature of the business. Okay, there were lots of other hands.
Can you discuss some of the science results of the 2 missions?
I can, yes. Let me just, I don't want to get into too much of it, because it was a general purpose observatory, and there were approximately 30 scientists, 10 or so associated with each of the 3 primary telescopes, and every one of those scientists had an observing program that would have filled up the entire 2 missions of the shuttle. And so we had to sort of try and figure out the optimum use of our time in orbit. And I'll just tell you about a couple. One is, I'm a planetary scientist of planetary atmospheres, and have been interested in observing the Io Taurus, the plasma torus around Jupiter, and had made some some sounding rocket observations of that. And so we did make some measurements of that, and we're trying to measure the atomic oxygen component, which is a tough measurement to make. And we were able to make some significant progress in that, so we measured that. But for me, that was an interesting one. For one of the reasons that HUT was selected in the first place was to try and measure the intergalactic gas, the gas between galaxies. And that is important because it has not been processed by stellar evolution. Anything within a galaxy has been processed by stellar evolution, which creates heavier elements. So the intergalactic gas should retain the signature of the Big Bang. Right? And there are very detailed predictions from particle physics about what that should be, and it's roughly 75% hydrogen, 25% helium by mass. The hydrogen component had been searched for many years, and it was finally determined that it's completely ionized, and so there's no way that we can see it, because the way we see it is by looking at a distant quasar and see an absorption feature that occurs, and if it's ionized, it's not going to see it. The helium component, however, singly ionized helium is a very tightly bound ion, and the wavelength that absorption edge would occur at was accessible to HUT, and that was one of the first instruments that was ever accessible, in orbit that could reach that. Because HUT, the short wavelength end of the spectrograph is at 800 angstroms, and this helium line would be shifted slightly above that, and so we weren't able to measure the helium component of the intergalactic medium and compare that to models and agree, precisely with the predictions from the Big Bang. And there were many, there were the first round of papers, or roughly 100 peer-reviewed papers that came out of the first flight within the first year. So it was a highly productive mission. Any others?
I want to hear about your experience here at LASP, Sam. Give us a memorable experience.
I thought I did.